In this video, we are going to talk about torque on a closed circuit in a magnetic field. In a previous video, we have proved that if we have a closed circuit in a uniform magnetic field, the total magnetic force on this closed circuit would be zero. And we said that although it is zero, it is not zero at all points of the circuit. In this case, there are some points has a force F and other points has force negative F. So the total force on the closed circuit is zero. But due to the arm between the force in the different points, there will be torque on this circuit. The definition of the torque, if we have a force and this force is acting on the point P, which is separated from the origin by radius r, so the torque of this force around the origin O would be the vector r coming from the origin to the point cross product with the force F, which is acting on the point P. So this is the definition of the torque. So if the force is normal to R, we have the maximum value of the torque, and if the force is acting on the same direction of R, the torque would be zero. This if the case was only one force is acting on the point P. Now assuming that we have two forces, force F1 and force F2 equals minus F1. And F1 is acting on the point P1 and F2, which is minus F1, is acting on the point P2. So in this case, the total torque around the origin would be the torque due to F1, which is R1 cross F1, plus the torque acting on the point P2, which is R2 cross minus F1. So by summing the two torques due to F1 and minus F1, it would be R1 minus R2 cross F1. R1 minus R2 is actually the vector from the point 2 to the point 1. So in this case, the total torque due to two forces equal in magnitude and in opposite signs equals the vector from the negative 1 to the positive 1, R21, cross product with the magnitude of the force F1, regardless if we are talking about the torque around the origin or at any other point. Because effectively, in this case, it doesn't depend on the origin only. So if F2 equals minus F1, then the torque would be R21, the vector coming from minus F1 to F, cross product with F, and it is independent of the choice of the origin for R1 and R2. So at any point, the torque of these two forces would be the same, because it depends only on the vector from the 2 points P2 and P1. Now, as I have mentioned, assume we are talking about uniform magnetic flux density. So the total force on a closed circuit would be minus I B cross the closed loop integration dl, and the closed loop integration dl equals 0, so the total force is 0. But this doesn't mean that there is no force. There actually force F1 minus F1. So any real closed circuit carrying direct current experience a total vector force of 0 in uniform magnetic field. However, the force is 0, or although the force is 0, the torque is generally not equal 0. And the torque in this case would be, I should collect the maximum force positive and the maximum negative force, and they should be equal. So the torque in this case would be R21 cross the magnitude of the force. As an example, assume that we have a closed rectangular loop inside the magnetic field B, general magnetic field B, and we are going to calculate the force at each arm of this loop, and based on the normal distance from the center of the loop to the origin, we can calculate the torque of each arm around the origin. Then we are going to calculate the total torque of this closed loop inside the magnetic field. We are going to assume that the current is passing counterclockwise, and this is x direction and this is y direction, and the length of this arm is delta x and the length of this arm is delta y. And B is general case, so B we have B naught, which is B naught x in x direction plus By naught in y direction plus Bz naught in z direction. So in this case, if we are talking about the first arm is directed in x direction. It carries a current I, so I delta x cross B is the force. So the incremental force 1 equals the incremental current 1 cross product with the magnetic flux density B. So IDL would be I dx in x direction cross B, and because the current is in x direction, so the components of the magnetic flux in this case, which will have non-zero value after cross product, would be By and Bz. So B naught y in y direction plus B naught z in z direction, Ax cross y would be Az, Ax cross z would be minus Ay. So delta force 1 in this case would be I dx By naught y in Az minus B naught z in Ay. This force has an arm or perpendicular arm to the origin equals dy over 2. So the torque due to force 1 at the origin, delta torque 1, would be the normal vector from the center of the current source or the current element, R1, cross the incremental force dF1. R1 is the distance dy over 2, and its direction is coming in the negative y direction, so it is minus Ay. So in this case, it would be minus half dy Ay, because I'm going against the y direction. This is y, this is x, and this is y. So I'm going here in the negative y direction. So negative delta y, ay, multiplied by delta force. Delta force is I dx, b naught y az minus b naught z ay. Y cross z is ax, y cross y is 0. So the incremental torque dt1 in this case would be minus half dx dy I b naught y ax. In a similar way, we can calculate the torque due to the element 3. In the element 3, the current is passing in negative x direction. And the distance here would be positive dy over positive dy over 2 in y direction. So following up the same steps for the arm 3, we can prove that the incremental torque on arm 3 would be R3 cross delta F3, which is half dy in y direction cross minus R dx ax cross b, and here minus because the current in this direction is negative with respect to this direction. So dt3 in this case would be minus half dx dy I b naught y ax, which actually is the same result as the torque due to dt1. So the summation of torque due to the arm1 plus arm3 would be this term plus this term. So dt1 plus dt3 would equal minus dx dy I b naught y ax. This half and this half is 1. Alright? It can be noted that these two arms has current in x direction, and the resulting torque is in x direction, and the resulting torque depends on the y component of the magnetic field b naught y. So if I have a loop in xy direction, the torque due to the current filaments in x direction would be in x direction, and the field component which will act on this torque would be the field component in y direction. So in a similar way, we can prove that the torque due to arms 2 and 4, which have current in y direction, here in negative y, here in positive y, the torque would be in y direction, and it would depend on the magnetic field in x direction. So d torque 2 plus d torque 3 would be dxy dy multiplied by the current I multiplied by b naught x dy. Should be noted here, this was with negative sign, this with positive sign, and this can be accumulated or explained as here the current was in positive x direction, here the current is in negative y direction. So the first arm here start with negative, here the current in positive y direction. So the current with respect to y direction in the arms 2 and 4 has a negative sign with respect to the current in x direction in 1 and 3. So this is the reason for here a negative sign and here without a negative sign. Okay. So the total torque in this case it would be D1 plus D2 plus D3 plus D4. So the total torque on this closed loop circuit would be I multiplied by dx dy, which is a common factor, multiplied by b naught x in y direction minus b naught y in x direction. So it should be noted that the magnetic flux b naught x here is in the vector y direction, b naught y here in the vector in x direction. Okay, so actually this is equivalent in vector form as az cross b naught. So the incremental work on this closed loop circuit would be I dx dy az cross b naught. But actually dx dy az is effectively the incremental surface vector of this closed loop. So we can represent it as the incremental torque would be the current on the loop multiplied by the vector surface area of the loop ds cross product with the applied magnetic field B. And we are going to define IDS as the differential magnetic dipole moment of the loop. And its unit would be ampere meter square. So the differential magnetic dipole moment dm, which is a vector quantity, and its vector quantity is represented by the normal vector to the loop carrying the current. So dm is I ds. So the incremental torque on the loop equal the differential magnetic dipole moment of the loop cross product with the magnetic flux density. In general, if we are talking about here what we are saying, delta T is I delta S cross B, so and delta M is I delta S, so delta torque is delta M cross B. So the torque on any planar loop of any size or shape in a uniform magnetic field instead of delta M would be the complete M. So the torque of any loop of any shape would be I S cross T, where IS is the magnetic dipole moment of this loop. Okay. So the torque on a planar loop of any size or shape in a uniform magnetic field is given by torque equals IS cross B or dipole moment M cross B. The torque on the current loop always tends to turn the loop so that it aligns the magnetic field produced by the loop with the applied magnetic field that is causing the torque. This is very important point. So effectively, any loop having a current will introduce a magnetic field normal to the loop. And the torque introduced in this loop introduced to rotate this loop such that the magnetic field of the loop is aligned with the applied magnetic field of the magnetic field outside the loop. So, for example, in the present case, this current is introducing magnetic field in that direction. And the torque on this loop is trying to rotate this loop such that it would be aligned along the lines of the magnetic flux. As an example, we have a rectangular loop carrying a current 4 milliamperes, and this loop has dimension 1 meter by 2 meter, 1 meter in x and 2 meters in y, and the loop is inserted in magnetic flux density equals minus zero point 0.6 in y direction plus zero point 0.8 in z direction Tesla. So the lines of the magnetic field or the applied magnetic flux looks like this. So in this case, the torque would be I S cross B, and according to the direction of the current, the normal vector of S would be positive Z. So in this case, I is 4 milliampere multiplied by the surface area, 1 multiplied by 2, and the normal according to the direction of the current is positive Z. So 1 multiplied by 2 in Z direction, cross product minus zero point 0.6 AY plus zero point 0.8 AZ. AZ cross AY is AX. AZ cross AZ would be 0. So in this case, the total torque would be 4.8 in x direction millinewton meter. When we are saying that it is in x direction, the torque in x direction, it means that as the loop is trying to rotate around the x, like this. So if we are saying that the loop is trying to rotate around x like this, it means that the magnetic field of the loop is trying to be aligned with the direction of the applied magnetic field. Okay? Alright.